Hi, my name is Yana, and I'll be presenting our work on assisting teaching assistants with automatic code corrections. So teaching assistants play a very important role in computer science courses. Students in CS courses can often get stuck on problems, and when they do, they usually require individualized help to get unstuck. Teaching assistants are often the first point of contact in that case for the students. But in order to help a student, the TA must, one, understand what is going wrong, and two, provide guidance to the student on how to fix it. This first part, understanding what's wrong, is the focus of our study. Understanding what's wrong, the first part, is a prerequisite for the second part, providing guidance, because if the TA doesn't understand, then it's going to be very hard for them to provide guidance that's actually helpful. But how do TAs go about gaining this understanding? How do they go about reading and debugging student code? Little is known about this. So in particular, what is difficult for TAs, what is not difficult, and what tools might be able to help them? To try to answer these questions, we conducted a study where we asked TAs to first debug student code and then write an explanation addressing the bugs. As part of this study, we wanted to evaluate whether seeing a generated correction can help TAs with these tasks. We reasoned that seeing a comparison like this might give TAs a sense of where the student was going with their approach by showing them a potential corrected version, and why they aren't quite there yet by showing them how the current student code differs from the corrected version. So quantitatively, we found that seeing a generated correction does help TAs. Specifically, it helps them debug the code faster. It helps them be more likely to find and fix the bugs of the student code. And it makes them more likely to address the bugs in the explanation that they give to the student. Additionally, we tested how seeing a problematic generated correction might affect teaching assistants. And we found that it makes them debug slower, but it doesn't seem to affect correctness in either finding the bugs or addressing them. Qualitatively, we also wanted to understand what is difficult for TAs in this task. In order to be able to answer that, we actually had all participants debug the same set of 8 problems. And each problem had 1 to 4 bugs in the student solution. We found that 3 of the problems consistently presented difficulties to TAs, and that the TAs were much less consistent in being able to address the bugs in those problems. But the other 5 problems didn't seem to present very many difficulties at all. And the interesting thing is that these 5 easy problems did represent a wide variety of bugs. So it doesn't look like there's any one reason for the easy problems to be easy. Rather, it seems like there are some very specific reasons why the 3 difficult problems are difficult. So in the interest of time, I'll just go over 2 of the interesting patterns we found on those difficult problems. So the first example is finding and fixing multiple instances of the same bug. And the second one will be addressing bugs that just have a single operator fix. So the first interesting bug is one where the student solution was missing parentheses in 3 near identical places in the same solution. Most participants, so most TAs fixing the bugs, found at least one of these parentheses, but only half of them found all 3 instances. Moreover, the participants who did find several instances tended to take fewer attempts, so less time to find the first instance than the subsequent instances that they found. We think that this indicates that participants did understand the error conceptually, or at least most of them did, but they had difficulty seeing the problem in the code, even when they understood the problem. The other interesting situation was with bugs that only required a change to a single operator to fix them. There were actually 2 such bugs in different problems where the only fix was to change 1 operator. And for each of these bugs, only about half of the TAs who fixed that bug went on to address it when they were writing the explanation to the student. Interestingly, these bugs were qualitatively different. One was probably a typo, and one was a quite serious logical error. And TAs did have more trouble fixing one than the other. But nevertheless, across participants, if you did fix the bug, you're only 50% likely to remember to address it in your explanation. So we think that this indicates that participants had a hard time remembering about a bug if they weren't able to visually see it in front of them because it's so small. And so the overall takeaways from our work are that TAs can have interesting and sometimes arguably unexpected difficulties when debugging student code. These difficulties don't seem to indicate a lack of conceptual understanding of the problem they're solving. We also saw that seeing a corrected version of the code does help TAs in their debugging tasks. But overall, more work is needed to understand why certain things are difficult and certain things aren't, and how we can best assist TAs in these tasks. Thank you.